Well, today we're going to be talking about definite integrals. Definite integrals are they're integrals we can actually find the value of their exact areas. So while last class we were doing Riemann sums where we were kind of estimating area, today we're really going to be actually finding that exact area of the curve. So we talked about this a little bit already. Our Riemann sums, those were ways to kind of evaluate area under the curve. It was very inexact. We use geometric formulas for those areas, so like the equation for a square, the equation for a trapezoid, that sort of stuff. So with definite integrals, we're going to explore geometric area a little bit more by being able to find exact area under curves that make those shapes. So let's look at an example. So for number one, for each of these integrals, we're going to sketch the region and then we're going to evaluate the integrals. We're going to be talking a little bit more about this interval notation. So in A, I have the integral from 1 to 3. So 1 to 3 is an x interval. So it's the integral from 1 to 3 of 4. So that means my equation is just f of x is equal to 4. So that's the equation I'm actually graphing. So f of x is equal to 4. That's just going to be a straight line through the y value of 4. So 1, 2, 3, 4. Just kind of give myself some room. 1, 2, 3, 4, 5, like so. I want to graph my line, my straight line through 4. And then my interval that I'm concerned with is that 1 to 3. So from x value of 1 to x value of 3 is where I'm concerned. So this whole area under the curve is what I'm trying to find. So you might notice it forms a rectangle. So that's a pretty easy area to find. So if I wanted to find that area under the curve, it would just be 2 times 4. So this integral would be equal to 4 times 2, which would be equal to 8. So the important thing with today's notes, y'all, is understanding that integral notation so you know how to set it up. And then remembering that the integral is the area under the curve. So we're going to be drawing those areas and then finding that geometric area under the curve. It's always the key common theme with all of our functions today is that they're going to be equations that we can find, nice shapes that we can find the area of. Okay. So B, we have the integral from 0 to 3 of x plus 2. So once again, just going to kind of add in. Well, I think I drew a bunch of squares there, but that's okay. I'm sure we can all forgive my terrible drawing skills. And then we have a line that goes through 2 with a slope of 1. 1, 2, so like that. And then I'm concerned about 0 to 3. So from 0 to 3. And this is the area that I'm finding. And of course, y'all, if you're struggling with these equations, use your calculator today so you can graph them. But you should be able to graph, the line 4 or the line x plus 2 pretty easily. Okay, so this one is, from what we can see, it looks like a trapezoid or a triangle on top of a rectangle. So if we remember from yesterday, our trapezoid equation is 1/2 times the height. So my height would be 3 times the 2 bases, so 2 plus 5. So that'd be 7 times 3, which is 21, divided by 1/2. So either 21 halves or 11.5. Either would be fine. Then over here on C, y'all, we have the integral from -2 to 2 of the square root of 4 minus x squared. Now, this one you probably don't know off the top of your head, but this is the equation for a circle, or because we only have the positive square root, only the positive half of that circle. So it is going to have a radius of 2 from that square root of 4. And it's just going to go and form that nice semicircle there. And then, of course, I'm concerned about it from -2 to 2. So boom, 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 boom. And so forth. Luckily, that basically includes the entire semicircle. And then this area in here is what I'm looking for. So the area equation for a circle is pi r squared. So since I want half of that circle, I'm going to do pi r squared times a half. So my area equation would be 1/2 pi radius squared. The radius of this is 2. So 1/2 pi times 2 squared. 2 squared would be 4. 4 times a half is 2. So this would be equal to 2 pi. And then D, we have the integral from 0 to 2 of the absolute value function x minus 1. So remember, an absolute value function is like, it starts as like a linear line, but it takes the negative portion of the linear line and flips it up to make that V shape. So the V specifically always hits wherever the x value is. So if I took the inside x minus 1 and solved it for x, I would get 1. So that's going to be where my V hits. So point right there. And then it's a slope of 1 for x. So it's just going to keep going up in both directions. Don't know what I did with that last one. Like so. Get your nice V. And then I am concerned about the area under my absolute value function from 0 to 2. That's the interval. So from 0, which is the y-axis, to 2. So you might notice I form these two separate little triangles. They both are the same. They both have a base of 1 and a height of 1. So it's just going to be 1/2 base times height. So 1/2 1 times 1 plus 1/2 1 times 1, which 1 times 1 is just 1. So it's 1/2 plus 1/2, which would be equal to 1. Which, if you look at that, you could probably say, oh, well, if I put those two triangles together, they probably form a square of size 1. So, makes sense. There we go. All right, so those are our definite integrals where we're drawing the shapes. We're finding areas under the curve of exact areas that we know, nice equations, squares, circles, triangles, trapezoids, your basic geometric shapes. Okay, so that's the first part of what we're talking about with definite integrals today, y'all. The second part is we're going to start learning some properties of integrals, some things that we always know to be true about integrals. So down here below are our properties of integrals. Kind of think about these as like your property of exponents or your property of logs. They're things I can do to manipulate my integral equations that I know to always be true. Same thing like with our basic derivative rules, like your sum difference, your multiplicative, derivative of 1, all that kind of stuff. These are sort of the same things, just but with integrals. Okay, so our first one, if f is defined at x is equal to a, then the integral from a to a of f of x dx is equal to 0. So what I want you to think about is, usually with all of our integrals, we have this distance that occurs, 0 to 2, 1 to 3, -2 to 2, this x distance. Well, what if my x distance is exactly just a point? Well, if my distance is just a point, there's not really area under the point because the point doesn't occupy any space. So what this is saying is that if my interval goes from a to a, so it stays in the exact same spot, then it's just the area under the point, which there is no area under a point. So that would be equal to 0. Okay? If f is integrable on the closed interval a to b, that just means I can take the integral, just like differentiable. Then the integral b to a of f of x dx is equal to negative a to b f of x dx. So what this means is that our integral always has to go from least to greatest. So when evaluating our integrals, we should follow the number line. We should go from smallest value to biggest value. So -4 to 7, 1 to 9. Okay. If we do it backwards, we need to fix it by switching the numbers on the interval and putting a negative in front of my integral. So really, really important. Just a pretty easy thing to figure out. Once you see it, if they're backwards, just flip them, put a negative in front. All right, if f is integrable on the closed interval a to b, the closed interval a to c, and the closed interval c to b, which that's just a really fancy way of saying there's a and b, which is our big interval, and then c somewhere in the middle. Then I can split the integral a to b into the integral a to c plus the integral c to b. So essentially, if I'm able to take my integral on my entire interval a to b, then I can split that interval at any point c along that interval. So let's say, just as an example, I can find the integral from 0 to 4 of f of x dx. Then I can split this into 0 to 1 f of x dx plus 1 to 4 f of x dx. So I can split any integral along its interval, that value c, somewhere in the middle, which is pretty cool that I can do that. And then the last two, y'all, should seem pretty familiar from what we've done with derivatives, because they're basically the same rules. So this is our constant multiple. If I have some constant being multiplied by f of x on the integral a to b, I can just move that constant out because I'm going to ignore it. I'm going to integrate it without really taking into consideration the constant, and then just multiply it back in at the end. So that's pretty cool. And then if I have the integral of two functions being added or subtracted, I can split it into two separate integrals of both of those functions still being added or subtracted. So that's kind of like our constant multiple rule with derivatives and our sum difference rule with derivatives. They're the exact same idea, that I'm going to ignore constants and then I'm going to keep addition and subtraction the same and integrate each function separately. Okay, so let's actually put these into practice a bit. All right, so I want to evaluate the integral from 1 to 3 of negative x squared plus 4x negative 3, given that the integral from 1 to 3 of x squared is equal to 26 thirds, the integral from 1 to 3 of x is equal to 4, and the integral from 1 to 3 of dx is equal to 2. Okay, so what I need to do is I need to get all of my pieces of my function to look like this. So the first thing I can do is I can split up negative x squared, 4x, and negative 3 into separate integrals. So then I can start trying to evaluate these three separate integrals. So this would become the integral from 1 to 3 of negative x squared dx plus the integral from 1 to 3 of 4x dx minus the integral from 1 to 3 of 3 dx. So first things first, I split them up, okay? Second thing I can do is notice how I have x squared, x, and then just dx. So I need to get these constants of negative 4 and 3 out. So just like my constant multiple rule, any constant k that's on the inside of the integral, I can move to the outside. So this becomes negative integral from 1 to 3 of x squared dx plus 4 integral from 1 to 3 of x dx minus 3 integral from 1 to 3 of just dx. Okay? So you might be like, Mr. Arbone, why did you do that? What's the point? Well, because I want to be able to replace these values that I know to be true. I know x squared is that, I know x is that, and I know dx is that. So now I can plug in x squared is equal to 26 thirds. So this becomes negative 26 thirds plus x is equal to 4. So 4 times 4 minus 3 dx is equal to 2. There we go. So now I have everything I need, and I can just simplify these numbers from here. So it's equal to negative 26 thirds plus 16 minus 6. So this becomes negative 26 thirds plus 10, which equals negative 26 thirds plus 30 thirds, which is equal to 4 thirds for my final answer. So all I did, y'all, is use my integral rules. I didn't actually integrate. Eventually, we're going to learn how to integrate that function by hand, but it's important that you can also use these integral rules, these integral properties, to be able to manipulate these functions. So we're going to practice with those first, so when we have to integrate this and also use our integral properties, we can do both. So let's look at this last example down here in the bottom. 3, given f of x, or given the integral from 0 to 3 of f of x dx is equal to 4, and the integral from 3 to 6 of f of x dx is equal to -1, evaluate each integral. So this is a real AP exam popular question, is this kind of giving you the integral of f of x and g of x and expecting you to be able to add and subtract them together, manipulate them based on your integral properties. Okay, so we're going to use our integral properties to solve all these out. So a is the integral from 0 to 6. So that's just both of my integrals put together, because I can split the integral from 0 to 6 into the integral from 0 to 3 f of x dx plus the integral from 3 to 6 f of x dx. So then I can just plug in what both of those are, which is 4 and -1. So 4 plus -1 is equal to 3. Nice and simple, just using my integral properties. So the integral from 6 to 3 of f of x dx, that's backwards, so I need to flip it. So this becomes negative times the integral from 3 to 6 of f of x dx, which is equal to negative. Integral from 3 to 6 is -1. Negative times -1 is equal to +1. Then C, the integral from 3 to 3 of f of x dx. Well, we know the integral from any number to itself, so the number doesn't change on the interval. That's just equal to 0. So that one's easy. And last but not least, the integral from 3 to 6 of -5 times f of x dx. So I got to get that -5 out. So -5 integral from 3 to 6 of f of x dx. So that's equal to -5 times integral from 3 to 6 is -1, which is equal to 5. All right, y'all. So that is the other half of 5.3. So our definite integrals, where we're finding areas, and our definite integrals, where we're just evaluating those integral properties, kind of starting to build that foundation of understanding what an integral is, understanding how to integrate before we get into our more advanced integrals for the rest of Chapter 5.